Today we are going to see the basic equations for linear motion when we have motion at a constant velocity or at a constant acceleration. Let's take a look at those and learn them in detail. So let me disappear from here. This is the objective is to find the kinematic equations for the quantities of position, displacement, velocity, and acceleration of a particle traveling a straight path. And we will look at the relations between the position, velocity, and acceleration for linear rectilinear motion, and also to the same when the acceleration is constant. So we have two conditions. The first one is here the motion of these objects can be characterized as a point mass motion, and we can analyze the motion of cars or rockets. In this case, if we measure the altitude, uh, can we determine the velocity and acceleration? In the case of a vehicle dynamics class or accident reconstruction class, it's important to see where every what's the location of every vehicle. Trains are also vehicles, but right now we are trying to understand the basic equations of position, velocity, and acceleration, and they could apply to a rocket, to an airplane, or to a vehicle, to a car. And in this case, the question is if we know that the train accelerates at a constant rate, um, what would be the position and velocity at that instance? All right, we we know that mechanics is the study of bodies, how body reacts with forces, and it's got two studies: the statics, which is the studies in equilibrium, and the dynamics. Dynamics is the subject that concerns us. We are on this in this area of the this is where we are on in terms of what we want to study. Um, excuse me. Let me see. Go back again. Um, this is the in the area of kinematics and kinetics. So this is only the area of kinematics is only the motion, the geometry aspect of motion, the position, velocity, and acceleration. While kinetics, this is the one that deals with the forces. These are the forces. Okay. So in the case of a vehicle, the accident, forces are important because forces either apply to vehicles or to people in cars. So when we look at the motion of a particle that moves the coordinate x is in this case the the position here is of the distance here is just the measure of the magnitude, but also the direction. So you could say a vector here. Vector has magnitude plus direction. So if we put a reference point and we say, okay, look, the particle is over here with respect to the origin. If this the the author uses s, but if we use x and y, then it follows that the measure from here to here, this is the this we could say the magnitude. This is s, but the vector is r. So r has magnitude and it also has direction. So that's why you see here r. Okay, measuring meters or in feet. In this case, the displacement is the change in position. So you could see that this would change from a, it would change. Let me just get the pen color change for a second. Okay, in color, so that we can see it a little nicer, a little better. So I just changed it to red. So you see here the position. This was the original position, and this was the change in position. So if you have delta r is the vector change, vector position change. But we are also interested what happens when the vector position changes over a period of time. And so this would be defined as the change in velocity of this. Yeah. So the total distance traveled by the particle is the total length. Yeah. The velocity in this case, we could define as the change of the position vector here, as you can see, as a function of time. This is defined as the average velocity. Okay, the instantaneous velocity is the derivative of this, of the position vector. So if we need to start with this very basic definition that the velocity is the change of the position, then we'll be able to understand the equations of motion much easier. So the average speed is the total distance traveled divided by the elapsed time. So we are trying to make the difference between what speed is and what velocity is. Speed is the magnitude of the velocity vector, right? So just as we're defining that the average velocity is delta r delta t. So this one is a vector, right? But this one here, this is a scalar because it's the measure of the magnitude of the vector. It's the total distance traveled divided by the elapsed time. So that is be the. What is the acceleration? The acceleration is the rate of change of the velocity with respect to time. So another way of writing what we have in here is that A is equal to dv dt. See? And in the previous one, we had that velocity was equal to dx dt, like this. And that will help us also derive the equations of motion. So the acceleration is in the vector form, is a dv dt. In the scalar form would be, in this case, the magnitude of the acceleration. It would be like this. All right? So it's positive if the speed is increasing, but it's negative if the speed is decreasing. So you could have an object moving in this direction, and let's say if this is a vehicle and you see a stop sign over here like this, the vehicle could have the velocity this way, but the acceleration would be the other way. That is important, because if the acceleration is going to be in the opposite direction as the motion, will have a negative sign. So that's what is important. These are the summary of the relationships that we will have, that we see in here. The velocity is the dx dt, the acceleration is dv dt, or the acceleration is b ds. I would like to expand on this a little bit. If you integrate the acceleration for velocity and position, you are going to basically enter the equations of motion. I mean, to find out the equations of motion. So if you integrate the acceleration, you will obtain the velocity. See, this is integration of the acceleration, obtain the velocity. If you integrate the acceleration as a function of the displacement, you obtain another equation. And the position would be the integral of the velocity. So to do this, you have three kinematics equations that do this. So well, first of all, let's review this. But this is what I was thinking to tell you how in the world this came about. And also this one, and also this one. Though I like to use X better. So let's just take a moment and let me go to my notes over here. And in here we will clarify this concept, okay? So this is just like I have the blank sheet of paper in here. I am going to write down that the basic concept that you have is the in here, that dx dt is the velocity, yeah. So we can actually write this way. Dx is v times dt, like this. So if b is a constant and we integrate this between x0 and x, and we integrate this between t sub 0 and t, you will see that this is the integral. This is like having a 1, right? So this is really x here, and you could write it like this, between the limits of x0 and x, and this would be b times time, really, because this is like also having 1, and this would be between t sub 0 and t. We normally have that t0 is 0, so this would say that x minus x sub 0 is equal to velocity times time, or finally would give us our velocity, our definition that x is equal to x sub 0 plus velocity times time. So this is one equation of motion that we need to know. Okay. if we look at the very basic concept of the definition of the velocity, we can very easily obtain this equation. So you could say that if x is, you could say, if x0 is equal to 0, then it follows that the position really is velocity times time. Okay, that's important because in certain parts of motion, we would have only this and no acceleration. So this is one derivation of the equation. So I would like you to have that. If we go ahead and look at the at another definition here, that dv dt is the acceleration, we can also write in an equal form that dv is equal to a times dt. So in likewise format as we did for the velocity, we can say that you can integrate between b sub 0 and b dv and integrate between t0 and t dt like this. So if this is true, very similar to the what we did before, you will have this, the integral would be b0 between the limits of b sub 0 and b, and this would be a times time between the t sub 0 and t, right? So if this is true, what we have is that, again, t sub 0 is equal to 0, so you have b minus b sub 0 is equal to a times t, or the equation that we need to know is that the velocity is equal to b sub 0 plus at, which is going to be the other equation of uniformly accelerated motion. Okay, so that's that one. Now there are two other equations that we need to know. If this is the, so this would be, I think it would be good to write down, this is uniformly accelerated motion. Okay, keeping this in mind, because when objects fall, or in the case of an auto rollover or an airborne vehicle, this equation has to apply because the acceleration of gravity, right? And also when the car slides on the surface, the friction force is proportional to the normal, and that normal is a fraction of the weight, right? So that's how the acceleration gets in there also. So if we know this, then we can go ahead and do another derivation. So I am going to put a line in here so that you can see this is a new one. So if we know this, isn't it true that the dx dt then is b sub 0 plus at based on this equation? And if that's true, then it follows that we could also write down dx is equal to b sub 0 plus at dt, and we can integrate this between x sub 0 and x, and then integrate between t sub 0 and t of this. So if you continue here, you will have that just as we did in the other equation, you can say that this is, see, you have like a 1 in here. So this is going to be x between x sub 0 and x. And then in here, this is going to be b sub 0 t plus 1/2 of a t squared between t sub 0 and t. So if t sub 0 is 0, then it follows that the position of a particle under uniformly accelerated motion would be, well, I think let's not rush. Let's x minus x sub 0 would be b sub 0 t plus 1/2 of a t squared. Yeah? So therefore, use therefore, it means that we have, this is x is equal to x sub 0 plus b sub 0 t plus 1/2 of a t squared. And that's the other equation of motion. See? That's why I wanted to show you where this came from, because I don't subscribe to the idea that we as engineers just memorize a formula. I don't like that. I think we need to know the details. In fact, some of these formulas, I don't remember them myself, but I know the basic concept where it comes from, and then I can actually do that. Now, the last one that I want is to say that you have that dv dt is equal to the acceleration, right? And we are going to combine the other one as well. We know that the dx dt, we know that dx dt is equal to the velocity. Yeah? So, isn't it true that we can actually, let's see, we can write down that dx over velocity is equal to dt, right? Like this. So if we want to express a relationship between, what do I write here? Relationship between the acceleration and the position, then it follows that I could replace that into this equation. This would be dx over v. See this dt that you see here, this one could be replaced by this, based on what I just did here, see? Okay, so this is the acceleration. Yeah, let's just do the same thing as I have done it in the past in there. The integral of v is going to be 1/2 of b squared between b sub 0 and b, and this would be ax, yeah, between x0 and x, yeah. So isn't it true that in here I could actually write this 1/2, I could take it out and say this is 1/2 multiplied by b minus b sub 0. This is equal to a times x minus x sub 0. Or we could say, okay, let's move this over here, and you will have b minus b sub 0 is equal to 2a times x minus x 0. And if this is the case, the velocity 1/2 of b squared, excuse me, like this, the velocity squared is equal to the velocity v sub 0 squared plus 2 times x minus x 0. So in this case, you can do this representation and have a expression for the final velocity based on the initial velocity plus the initial position. See? So this is the other equation of motion. I think those are the three equations of motion that I wanted to review with you and show you exactly where they came from, making a summary from the definition of the velocity. If we integrate, we get this equation, which is x is equal x0 plus b sub t. From the definition of the acceleration, we obtain that b is b0 plus at. And going back to and using this expression and integrating it in on one side in x and t on the other side, we obtain the other equation of motion, which is x is equal x0 plus b0 t plus 1/2 of at squared. And finally, just a little bit of a transformation of variables here, a relationship between the velocity, acceleration, the displacement, but no time. But of course, we know that time is involved in here. But those are the equations that you saw were expressed on the slide over here that we had the, see, this is the one expression, the other one, and the final one that we see. Although the author, Hibbeler in this case uses S, I like to use X. So that is the explanation of those three equations.